Okay, welcome to University of Texas, San Antonio, in San Antonio, Texas. My name is Mo Jamshidi, and in this course, we are looking at manipulated robotics and mobile robotics, quadcopters, and so forth. So let me go to my station and start from there with the first lecture, which is the introduction to robotics. Okay, again, this is my email addresses. I would prefer the first one because this is much easier access to me than the second one. And we talked about intelligence in terms of control theory. We talked about robots which can think. We call them intelligent robots, and mobile devices. And we also talk about quadcopters, unmanned aerial vehicle, and in some projects, underwater robot. So the subject of robotics has a long history. It doesn't look that way, but it has a long history in terms of the concept, but not the real actual application in industry. It can go back to the 12th century, or in the 15th century, Leonardo da Vinci's robot Knight, which bridged the gap between mechanical and anatomical study. In 1921 time frame, there was a particular actual theatrical show in today's Czech Republic. And a gentleman by the name of Karel Čapek produced a bunch of what we now call humanoid robots as players in the play. Okay, and in that sense, the word robot first started from that point on. Again, you can help yourself going to a specific website. We don't have enough time to go through each individual one. Then we had, in the 1940s, during the World War II, and places like Oak Ridge National Lab in this country, the concept of teleoperation, master-slave came into being, because handling nuclear material, for whatever reason, whether it's electricity or weapon or what have you, you cannot do unless you have a robot inside secured radiation resistant environment. For that reason, you need an operator, a human, to operate a master robot to handle the slave's behavior through a window and through a camera. So this is actually what happened in the post-World War II. In 1950s, numerical control machine was invented by a gentleman called John Parsons, and this was later on led to an articulated robot of a gentleman called George DeWall, who was actually a graduate student of physics at Columbia University in the 1950s. And later on, you know, one of his classmates by the name of Joseph Engelberger, who unfortunately passed away December 1st at the age of 90. He is considered the father of robotics, especially industrial robots. In 1960s, Puma was the robot that Joe Engelberger manufactured in the United States. In 1967, he actually went with the first class ticket with Japanese, went to Japan to show Japanese what the robot is, and gave them a license. And Yamaha and many other companies started, and they have really boomed on that. So there are several definitions of a robot, but the two main ones are robot manipulator and mobile robot, or rovers. And as I said before, it's a bit more general than that. You know, even anything any machine, you can program it, and and then let it run by itself is a robot. Okay? It could be even something you can do with your devices at home. You can program, a toy machine that you can run it by your cell phone and WhatsApp. So a robot is a reprogrammable, multifunctional manipulator designed to move material, parts, tools through programmable motions to perform a specific task. And it involves a multidisciplinary areas: sensing, control, intelligence, computing, now cloud computing, artificial intelligence, of course, image processing, vision, and so forth and so on. The recent definition is a machine that senses, thinks, and acts. This is the definition in your textbook. A machine that senses, thinks, and acts. A robot needs to sense information from environment, use it to actuate something to happen, like a human reflexes for reactions. This is equivalent to the first definition. The distinguished point here is that mobile robot is used intelligence to emulate more type of cognitive behavior. A big difference between manipulated robot and mobile robot is that the manipulated robot, as you already know, is stationary, is installed in the factory floor or in your research lab, and it's not going anywhere. It's staying there. And its workspace, so-called workspace, which you learn what it is later, is limited. You have something that you can extend going somewhere around, and that's all you can do. You can't go there with that robot. Okay? Mobile robot, on the other hand, goes anywhere it possibly has to. So it's not fixed to the ground. And that makes it much more challenging, because you need to basically know the robot to understand where it's located and where it's going to go from point A to point B. Okay. Here are the two definitions. On the left, you see a manipulator, which is one of the Unimate original Puma robots. And this is the Mars robot for the Caltech Jet Propulsion Lab, contracting with NASA. This is the actual one. And industrial robots applications are welding, painting, materials handling, manufacturing, so forth, medical applications. You can have the robot work hand in hand with the surgeon and do precision surgery. Okay? And the good thing is that robot is not shaking the hand like a 65, 70-year-old. Okay? So that's the point. You could have entertainment. All the robots you see in the Hall of the Presidents in Disney World is a robot. Okay? Which talks, moves, sits down and gets up and so forth. Of course, a space robot, you just saw an example of it. Education, you are in it right now. And it's quite popular. Robotics has been pretty much popular for the past 30 years. Military applications, you have robots which are in the backpack of military soldiers or Navy SEALs and others, and they actually are there to help the mission. Okay. Not to mention the drone, which do so much already. Reconnaissance is obvious. Hazardous material handling, such as nuclear material and nuclear power plants, and so forth. In the area of entertainment and toys, you can have, for example, two toys like this, which came from Japanese manufacturer Sony. In the 1990s, and still to some extent nowadays, there's a huge international competition called robot soccer competition. I used to have a team in New Mexico, which would go to conferences and compete with Koreans against Koreans and others. Okay, and you can see that in fact Patrick Benavides has already built 4 soccer robots, and you can, when you visit the ACE lab later on this week, you will see all those things. He also has built 4 sumo wrestling robots, which you can put one robot fighting another robot in a constrained domain on the floor, and the one who pushes it beyond the boundary is wins. Okay? And it works autonomously. Here is a famous humanoid robot in Honda motor. As you can see, it probably looks on the left, looks like probably a meter and a half or so, or maybe a meter and 20 centimeters. And it's called Asimo. And Honda uses it for basically public affairs and for promotion. And for example, it played soccer with President Obama in Japan last time. He was there. Okay. This is the robot we are going to build. This is Poppy humanoid robot, about 85 centimeters. And this robot, which we are going to order soon, has an option that you would be, you can actually order a more expensive version of it with all the things printed for you. Since we know how to print, and you are going to help print a hand, print a head, you can print many different things. Even before the robot arrives, we're going to start doing that. Then we get a cheaper robot, we can build it ourselves. Hopefully by the end of semester, you are going to do some work on it. Again, 2 industrial robots. These are 3 mobile robots. The robot in yellow is actually a Pioneer robot. We have 2 of those, which I brought from my previous job. And we can do navigation. It's going to be part of your experiment. Yeah, our robot looks like the red ones, and we can do those kinds of robots. The robot on the right is a people bot, and I've seen that actually going through wards of hospitals, goes to the patient's room and actually reports the vital signs of the patient to the doctor who's in his home. Okay, and the doctor can basically see what's going on for his or her patient without being at the hospital at the given time. These are the Roomba vacuum cleaner robot. I think it's getting more expensive than what I have here. And interesting that the robot that Patrick did for his part of his PhD in ACE Lab #1, he bought a platform of a Roomba, I believe, on eBay, and for about $35, and he built 3-4 floors on it, including a 5 degree of freedom robot. This is part of the project. So you can work with Patrick on that particular robot for what we call assistive robotics. And if you go to ACE website, you see that's part of one of our core competency. Here's a snake robot, something that Ikram is building, and Ikram, I believe, has on order all the motors and all the materials he needs to connect the links together. Every link of that snake robot is a system, is a control system. You're dealing with 11, for his case, 11 control systems at the same time. And they all have to be controlled in a coordinated manner. And I was promised by him that the first few links are going to come up and greet you like a cobra. Okay? And we're going to actually, I'm requiring him to put two cameras and lights for their eyes. Okay? Otherwise, he won't graduate. So, this is the snake robot. In fact, this is a simulation which came out of Carnegie Mellon several years ago. This is what we don't do. We don't do walking robots right now. Okay, I used to do that in ACE Lab. But locomotion is a somewhat tough task. You see, you have to. Of course, when the humanoid robot is, we do have locomotion. It comes with the robot, so you will learn it in that way. But this is a four-legged robot, which is part of the Hiroshi Unida Laboratory in TIT, Tokyo Institute of Technology. There are robots which you can basically fit in the bottom of your hand. The one on the left is one of those, Chepera, which is, I used to have 2 or 3 of them in New Mexico. And another one, which is the K-Team robot. These are all coming from a company in Switzerland. I don't have those in the lab. Again, industrial robot, Puma 560. Hand, we are going to be printing hand for the humanoid robot that Berat is working on. And this is a Utah MIT hand, which is, as you can see, it says four finger, and the robot hand that we've already had a small print of it. I forgot to bring it to show it to you. It's in my office. It's going to have a motor to actuate 4 fingers together, and another one for the thumb. So with combination of those 2 actuators, you can pick things up. Okay. Of course, this is the Mars Explorative Rover and the Canada arm, which built by the Canadian Space Agency as part of the consortium of the International Space Station. When I was the honor of consulting or advising NASA, I've been to every single NASA center in the country already, from Kennedy all the way to the West Coast there. And it's so much fun. If you want to work for government, work for NASA. And I used to think if you want to work for industry, work for IBM. Okay? And these are the 2 desirable places. Of course, now IBM is given that to many other companies in the Bay Area. So you can have robots working like a swarm. This is something that we have built more than once or twice in ACE Lab. Robots will work together as a team. Okay. We once built 3 small robots. We put the algorithm of the way the bees in biology and in nature behave. So a bee goes to a particular flower and finds the right nectar, and then inform the others to go, and that's what the robots will do. Okay, and we have many other ways that we can do that. In fact, we have now in the ACE Lab, we have 4 research groups which are working on swarm of heterogeneous robots. By that I mean swarm of a land rover, underwater robot, and a quadcopter, all 3 working together. You can see how far you can go with that kind of paradigm and that kind of situation. You probably remember and know that DARPA, the research wing of the Department of Defense, several years ago, gave $1 million reward to an autonomous vehicle to go from outside of Los Angeles all the way to Las Vegas. Okay? And the first year or 2, nobody was able to complete the mission. But finally, a Stanford group from Stanford did it. And I don't know for sure, but I think that DARPA initiative went a long way. Now we have driverless cars built by Mercedes, by Google, by GM, many other companies are now doing it. Okay. So your grandma can go shopping without any driver. Okay. Medical robotics. And as you can see, your MRI machine, your CT scan machine are really robot. They're programmed to do something and move around and do something for the patient. Okay. And on the left you see a cartoon for a manipulated robot which works on the body of a patient. A lot of work going on at UCLA Medical School are used medical robotics. And they're getting a lot of technology transferred from JPL in Pasadena to Westwood in the other side of the town. In one of my trips to Australia, I was lecturing at a national laboratory in Australia, in Brisbane, Australia. This is one of the robots in that national lab. I forgot its name. And it's quite sophisticated. And they would put it into a huge sort of pool with all kinds of things on the floor and so forth. And this is, in fact, ironically, one of my Australian visiting students, Ben, that is not here. You will meet him in the ACE lab. Ben has a team that is in the table. You can join him, Ben, and another couple of other students. And he has a project which allows the underwater robot to find and recognize an object under the water on the floor, and has its own mechanism, manipulation underwater to pick it up, bring it to the edge of the, let's say, swimming pool, and at the same time informs a Land Rover outside to come and pick it up from the water. This is what he wants to do, part of his PhD at Deakin University in Australia. And I've hosted, he's number 4 student I've hosted here at UTSA, doing their research here in ACE lab. So remember his name is Ben Champion. He's already got a nice last name. Okay. So here is another one. Triton, of course, these kind of underwater robots are the ones who go and look at Titanic's material down in the ocean, that they brought a lot of things. A few years ago. Another quite commercial one is another one, Argus. Last summer, I was in one of the islands of Hawaii, and I ran into an octocopter here, which is priced at $20,000. Our quadcopters are nowhere near that. And it has a camera underneath, you see, and it was hovering over Pacific Ocean off the coast. There was a pilot which was handling that, and there was a cameraman who was taking photos, commercial type of photos, which would actually sell it to the rest of the world. And you can see it hovering in the air and taking photos of this water jumping out of the ocean. You see it up there here, and this water coming from the ocean and shoots up like a big flash, or like a geyser, in a national park in Wyoming. So ACE lab facility, this is courtesy of Patrick. What we have plenty of things. For the past 10 years, I probably put at least $800,000 in these labs. Okay? And we got Kinect vision system. We have a Mars yard. We have 6 tendon IP webcams. We have one loosebot TAZ4 3D printer. We have another Upbox 3D printer. We have a double pendulum that you're going to be working with, 2 Pioneer robots you're going to be working with, and a whole bunch of robots that we bought the tracks, and the students built everything on it. Okay? And Patrick had done about 15 of those things in the lab. So while he's in the ACE lab, take advantage of pick his brain, but know what you are asking him. Okay? If you just want a spoon-fed, don't even near it. So here is the rest of it. I'm not going to bore you with it. Let's go to, we now have a 10 open compute project. We want Facebook cloud server, we call it ASPAR. You're going to be using that. And Patrick is hopefully soon going to be finished installing all 10 servers in the ACE lab. And with the help of Ali, you know how to program on the cloud, work on the cloud. Here's the scene from ACE lab number 1. You're going to see it. We're going to open it on Thursday afternoon and Friday afternoon. I'm teaching a course at 4 o'clock on Friday, but before that. And incidentally, I'm teaching a course on machine learning, big data analytics, and cloud on Fridays. For the gas lectures, the two student groups are going to merge together. And they're going to join you because you're going to learn together. These are some of the robots that have been built. For example, this is a robot which one of the earliest ones. We built about 8-9 years ago. And this is the first robot which we built by a former student of mine from India, who is now a robotic engineer in a startup company in Houston. These are the two robots in the grass in front. Last year in the robotics class, we had a 3D printed robot. And you can see it. And a project on the list is on it. And another student, Eric, led the way for that last year. And his work and his autonomous behaviors and all the testing he did, as you can see, the robot has a circular blue color end effector. It goes in front, lines up with this valve and opens the valve. Okay? We'll show you the video of all these things. And this became viral last summer on YouTube. And Eric got quite a bit of really mileage out of it. Not that he intended to have it, but it was just what happened. And then another student, Jonathan, another Air Force student, made this voice activated. So you'll see video on that. So you can work on that and improve it, and Jonathan and Eric also will hopefully be there to help. This is the assisted robotics of Patrick that you can see. And right here, this is that Rombo vacuum cleaner. The rest are all what he has done. And one of the nicest things he has done is he has several different designs of an end effector. This orange color end effector. Sometimes 4, sometimes 5, sometimes 6 fingers. It can pick up your credit card from a flat floor. Okay? Maybe I put that as part of passing the course. I don't know. But I'm just teasing. Okay? So, it is, for example, the robot is moving from picking up a roll of tape and putting it into this plastic box. So, again, these are some of the graduate students and Dr. Benavides. This is ACE Lab number 2, which you can visit. Here is the smart walker. Some of you will be working on it. And what Eric is going to be doing and helping you, right now he had to move fast to defend his master's thesis. He made the seat to be his platform for all the electronics. So what he's going to be doing, and we hope that the team will help with him, print a circuit board for the entire thing which is on the seat, put it under the seat, and we use the seat the way it's supposed to. Here's the UOTSA cloud and the Open Cloud Institute. We're going to get just, our fog is going to be just a small piece of this kind of structure. These are the list of projects that you see it also, you saw it in your outline of the course, the syllabus. I want the name of the students, each and the student and his or her partner, no longer than Friday. Remember, if you don't jump on the project, it's like you're failing a quiz, you're failing part of your midterm. It's that serious, okay? Because there's no other way except for the homework I can engage you, okay? So you need to take that very seriously. So that's the end of this lecture, and we'll take a short break, and then we'll go from there.